Hello, everyone. Welcome to Introduction to NoSQL Databases. Before we dive into specifics, let's clarify what we mean by NoSQL. The term NoSQL stands for not only SQL and generally refers to a broad class of non-relational databases that are designed to handle data differently from traditional SQL-based systems like MySQL, Postgres, or Oracle. And historically, relational databases dominated the market. However, with the increasing need to handle massive volumes of data, higher throughput, and distributed deployments, new database solutions emerged, collectively grouped under the NoSQL umbrella. And most NoSQL databases do not rely on fixed schemas like relational databases do, and they are built to scale out horizontally across clusters of machines. They're designed for flexible data models, allowing documents, key value pairs, wide column structures, or graphs. It's also worth noting that the name NoSQL can be misleading. Some interpret it as no SQL at all, but a better way is to read it as not only SQL, meaning these databases can sometimes include some SQL-like query capabilities. Why no SQL? So why do we need no SQL? That's a reasonable question if you come from a background where relational databases have been the standard. Let's take a look at a few reasons. First, scalability. So relational databases often rely on vertical scaling. That means upgrading to bigger servers when more data or higher workloads are required. NoSQL databases, on the other hand, typically allow horizontal scaling where you distribute data across multiple commodity servers or nodes, making it more cost-effective and easier to manage when your application's data volume or user load grows significantly. Next is performance. A lot of NoSQL solutions are designed to maintain low latency and deliver high throughput, especially under huge volumes of read and write operations. And this is important for real-time and near real-time applications such as social media feeds, e-commerce product catalogs, and IoT sensor data. Third is flexibility. Traditional relational databases require a defined schema upfront, and if you need to change the schema later, it can become a pretty disruptive process. NoSQL databases often adopt a schema-less or flexible schema model, meaning you can store data in the way that suits your evolving application needs. And this approach is a big advantage for agile development where requirements may frequently shift. Last is rapid development. Since you don't have to worry about complex table structures and joins, you can focus on building features more quickly. The NoSQL data model can match the objects in your application code more naturally, especially if you are storing documents or key value pairs. Types of NoSQL databases overview. NoSQL is an umbrella term covering many different database types. While they share some core principles, such as flexible schemas and horizontal scaling, the way data is modeled and accessed can vary widely. And here is a quick overview of the most common NoSQL database categories. First is key value store. This is often viewed as the simplest form of NoSQL database. Each record is stored as a pair consisting of a unique key and a value. Next is document store. And these document store databases store semi-structured or unstructured data as documents, typically in JSON or BSON formats. Next is column family store, and these are sometimes called wide column stores, and these are built around column families rather than rows, making them extremely efficient for analytic queries on large data sets. Graph database, they are designed to store and traverse complex relationships, and these databases model data in nodes and edges, which is particularly beneficial for social networks or recommendation engines. Other specialized databases, this includes time series databases specialized in chronological data or search engine oriented databases that focus on text indexing and retrieval. Let's go over each. And first is key value databases. And key value stores are the simplest form of NoSQL databases. Each entry in the database consists of two parts, a unique key and a corresponding value. You can think of it like a hash table, but is distributed. If we first talk about data model, let me give you an example. Say you have a key like user with user ID, user, and the associated value might be a JSON blob containing user information or something else entirely. The database doesn't really care what's inside that value. It only sees an opaque chunk of data, and this simplicity can lead to very fast read-write operations since there is minimal overhead, especially if the database holds data in memory, as with Redis. And performance and use cases, key value stores excel in caching scenarios where you need to quickly retrieve data by a known key. They are also great for maintaining state in microservice-based architecture. For example, if you need to track session data for millions of online users concurrently, a key value store can handle the load with low latency. And some of the popular options are Redis, which is an in-memory data structure uh, that provides ultra-fast reads and writes. Amazon DynamoDB is another option that is a fully managed AWS service that implements a key value, but also partially document-oriented. Uh, React is another distributed key value system known for high availability. So key value stores are straightforward but extremely powerful when used appropriately, since they often serve as a backbone of caching layers, real-time analytics, and ephemeral data storage. 리코딩을 그 하고 있는데 잠깐 퍼즐했어. 그래서 그냥 들어오면 돼. 편하게 들어오시면 됩니다.
책 되게 인기 있네. 도서관에서 말볼 때 많이 팔았다고 보니까 지금 웨이리스트에 들어가면 한 16주 걸리네. 진짜요? 그거 저랑 오시고 하면 되게 웃겨요. 그리고 약간 어, 되게 현실적인 그 젠지 특유의 그래서 그 추천할 리뷰가 웃겨갖고 그런 그런 나한테 가면 우리한테 쓰는데 말씀 티라 아니 그래 그래서 이 저는 그때 다음 주고 해서 넘겨주고 아 풀라고 하나를 딱 없애는 거를 되게 좋아해요. 거기다가 맨날 스위치하는 스위치하면은 하고 빨래 꺼내다가 드라이기도 해야 되는데 까먹고 못 가고 맨날 내가 다른 거 해줄 거야. 내가 아니 내가 할게 하면 저기 이러고 그러면 이것만 마저 하고 아 근데 남친분이랑도 가시는데 여기 또 오셔서 진짜 안 가봤어요. 그래서 안 가봤어요? 다른 건 몰라도 너랑 처음 코치로 같이 가는 거를 기념을 만들어야겠다. 내가 막 그래서 멋지지 멋지지. 약간 누가 오늘 진짜 보여줘. 자기의 가장 바다를 보인다. 하고 그 다음에 바로 하겠습니다. 상관없어요. 이렇게 있어도 돼요. Document databases. Document databases store data in the form of documents, commonly in the format of JSON, BSON, or sometimes XML if you have legacy system. And each document contains the data itself and sometimes metadata about that data. And let's go over data model. And the biggest advantage of document databases is the flexible schema,
which means you can add new fields to a document without having to restructure your entire database, like relational databases. This is beneficial for agile development and for storing complex nested data structure, especially. Just to give you an example, let's say we have a products collection with documents that each describe a product. Then if we add a new optional attribute like color, we can do so on a single document basis without adding that to all documents. That means we don't need to disrupt existing product documents that lack the color fields. For use cases, document databases are popular for web applications that frequently exchange JSON payloads. You can often store data in the same format you receive it and retrieve it in the same format for display, which is really powerful. And document databases are highly convenient for content management systems, catalogs, and any system where the data structure can evolve over time. Uh, in terms of document database options, MongoDB is perhaps the most widely known document database, supporting a rich query language and indexing features. CouchDB focuses on a RESTful JSON API with easy replication and offline first concepts. Firebase Firestore offers real-time synchronization across clients and flexible JSON-based documents. So document databases uh, position themselves between relational and pure key value databases, and they preserve some structure like fields and nesting, but without the rigid schemas of relational databases. Moving on to column family databases. Column family databases, sometimes referred to as wide column stores, store data in a schema that focuses on columns rather than rows. And this concept first uh, came from Google's Big Table paper. And this paper influenced many open source projects like Hadoop, HBase, and Apache Cassandra. In terms of data model, uh, so this database is storing a row across, this database is not storing a row across multiple columns in a single table. Instead, data is grouped into column families where each column family can host many columns. For example, you might have a column family for user profile data and another for user preference. Each user row can have a variable number of columns in each family. And if we look at scalability and use cases, and these systems are highly distributed and built to handle petabytes of data across clusters with thousands of nodes, and column family stores are particularly popular for analytic workloads and scenarios where you need high write throughput and linear scalability. And for column family databases, Apache Cassandra is known for its decentralized masterless architecture. And by having this uh, architecture, it makes the database incredibly fault tolerant. And HBase sits on top of Hadoop's HDFS, and it integrates nicely with the broader Hadoop's ecosystem. And thanks to their design, column family databases can handle massive data volumes efficiently, making them a great choice for big data analytics and real-time applications that need consistent high performance at scale. Moving on to graph databases. Graph databases are specialized in modeling and traversing relationships. So instead of the row and column model, data is stored in nodes, and nodes representing entities, and edges representing relationships between entities. If you go over examples, we can talk about social network. So if you're to have social network and graph database, each node might represent a person, and an edge would indicate that two people are friends. And graph databases are naturally adept at queries like what is the shortest path between person A and person B, or who are the common friends of person X and person Y. So you can store properties on both nodes and edges, which allows for complex queries about relationships in a way that would be very difficult in a relational databases. And for use cases, graph databases shine in contexts where relationships are paramount, such as social networks, fraud detection, and recommendation engines. So, for example, say you want to build a recommendation system that suggests products based on a user's purchase history, browsing behavior, and social connections. A graph database can handle that complexity more gracefully than a table-based approach. And for popular graph databases, Neo4j is one of the most established graph databases, offering its own query language called Cypher. Amazon Neptune is another option. This one is cloud-based graph database service with support for both RDF and property graph model. So graph databases represent another dimension of NoSQL data storage, the ability to quickly and efficiently query and navigate relationships. And this opens up new possibilities for applications that rely on connected data. Moving on to ACID versus base. And this is the core distinctions between relational databases and many NoSQL databases uh, in terms of handling consistency and transaction. Let's first talk about ACID. Relational databases typically follow the ACID properties, and ACID stands for atomicity, consistency, isolation, durability. And these properties ensure that transactions are processed reliably. To give you an example, let's talk about a bank. If a bank transfer transaction, uh, it's possible that the transaction could succeed, but sometimes that transaction can fail. And say that transaction fails halfway, then this could cause uh, balance to be in an inconsistent state. So by having relational databases property, we can have the entire transaction to be rolled back, which leaves the database in a consistent state. Now let's talk about base, because many NoSQL databases follow a base approach. Base stands for basically available, soft state, and eventual consistency. What does this mean? This means the system guarantees eventual consistency, not just consistency, it's eventual consistency, which means unlike um, relational databases following the uh, ACID property, all replicas may not contain the exact same data, but it will eventually. Um, to kind of delve more into eventual consistency, uh, say no new updates are made to a given piece of data. This means that all the accesses to that data will eventually return the last updated value. This design is often chosen for large, distributed, and high availability systems. And this has trade-offs because because you are gaining availability and scalability, but you lose the strong consistency guarantees of asset transactions. And in many internet scale applications like social media feeds, unlike bank transfers, the absolute real-time consistency is probably less critical than being available for reads and writes across multiple regions. So when evaluating a NoSQL database, think about how critical strict consistency is to your application. If your use case allows for some level of eventual consistency, NoSQL solutions can offer significant performance and scalability benefits. Moving on to use cases and best practices. With so many NoSQL types, you may wonder what what is the best way to pick the right one? And this answer depends heavily on your application's requirements. So you want to identify the requirements of your application. First is uh, you want to ask yourself, is your data mostly key value lookups? And if that's the case, a key value store might be simplest and also fastest. What if your data is semi-structured or it's JSON-like objects? If that's the case, then document databases are often ideal. If you have a uh, data set that is massive, but at the same time requiring real-time analytics, column family stores can be a good fit. If your use case is heavily relationship based, a graph database often provides the best model. And let's talk about cap theorem and balancing the cap theorem. So the cap theorem states you can only strongly optimize for two out of three. And what are those three that we're talking about? They are consistency, availability, and partition tolerance. And with distributed systems, partition tolerance is usually a given. So you end up trading off consistency and availability. And polyglot persistence. Uh, so in complex applications, uh, one single database type might not fit all scenarios. That's where polyglot persistence comes in. You use different databases for different parts of your system based on which type suits a particular workload. So, for example, you might use a document store for user profiles, a graph database for relationships, and a relational database for billing transactions. To talk about, to give you example deployments, e-commerce websites often use NoSQL for product catalogs, session management, and real-time analytics. IoT solutions rely on time series or key value stores for handling large numbers of sensor data at scale. And social media platforms usually incorporate graph databases for friend follow connections. So you want to carefully look at your query patterns, data volume, and operational needs before choosing a NoSQL solution. Future trends. Let's look ahead some future trends and summarize what we've learned. Uh, First is multi-model databases, and the lines between different database types are blurring. So some databases offer document, key value, and graph capabilities all within a single engine. And this gives developers more flexibility without needing multiple systems. Evolving query languages. A lot of NoSQL databases now offer SQL-like query capabilities or are working on bridging the gap between NoSQL data models and traditional SQL queries. And this helps reduce the learning curve for teams already familiar with SQL. Hybrid cloud and edge computing, as many organizations distribute workload across on-premises data center, public clouds, and edge locations, NoSQL databases that can run and sync across these diverse environments, and they will become increasingly important. Conclusion, NoSQL databases have emerged as a response to modern data challenges, emphasizing scalability, performance, and flexible schema designs. And there are different NoSQL models, such as key value, document, column family, and graph. And they each solve different types of data problems. And the choice of a NoSQL database should be driven by your use case, including your needs for performance, consistency, and the shape of your data. Thank you, everyone, for listening.